Have you ever heard of an AI underdog story? Because that's exactly what we're seeing with something called test time compute. Imagine a smaller, less powerful AI going head to head with a model 14 times its size and winning. Sounds unbelievable, right? But it's happening, and it's changing the way we think about AI. We're about to explore how a simple idea, giving AI more time to think, is revolutionizing the world of artificial intelligence. Quick reminder from our last video. Test time compute is not about retraining your AI. Forget about feeding it mountains of more data. It's about giving AI extra processing power during inference. That's just a fancy word for when the AI is actually doing something, like answering a question, solving a problem, or generating text. Think of it like giving the AI a mental workspace, room to explore different options, or an internal debate stage, all inside its digital brain. And this basic concept isn't entirely brand new. Models like Anthropic's Claude have been using a form of thinking tokens for a while. But what is new is the scale and sophistication of the techniques we're seeing now. We're talking about a whole new level of AI reasoning. No more just spitting out the first thing that comes to mind. These AIs are deliberating. But first, let's back up a bit. For years, the AI world has had one mantra: bigger is better. More data, more parameters, more everything. And it worked for a while. Bigger models did get better results. But now, we're facing some serious challenges. Building these giant models is incredibly expensive, and it takes massive amounts of energy. And we're even running into limits on how much high-quality data we can feed them. There is debate about if we're starting to see diminishing returns for all that extra cost and complexity. So the big question is, what now? What's the next breakthrough? That brings us to why test time compute is becoming such a hot topic right now. It's not just about bigger, it's about smarter. We've reached a point where simply throwing more resources at the problem isn't the most effective solution. Maybe we haven't hit the limits of scaling yet, but there are other factors too. We're developing better techniques for using that compute during inference. And frankly, we need more reliable and explainable AI. Plus, building these massive models isn't an option for everyone. It takes serious resources. Which is one reason some researchers are also putting effort into making smaller, open source models more powerful using techniques like test time compute. Now, you might be thinking, this all sounds great, but it's probably only for big tech companies with huge budgets, right? Wrong. And that's one of the most exciting parts of this whole story. But before we jump into that, let's examine the core technology. So, how does this thinking actually happen? What are the specific techniques that allow an AI to go beyond its initial response and improve its answers? Get ready, because we're about to explore some seriously clever methods. Let's start with beam search. Imagine the AI isn't just considering the single most likely next word in a sentence. It's considering the top several possibilities, all at the same time. It's like planning a road trip. One AI might suggest the fastest route. Another might prioritize scenic highways. And a third might look for the route with the best restaurants. Beam search considers all of these, then picks the most promising options to explore further. But instead of letting them all run wild, we keep only the best paths and discard the rest. This beam of possibilities is constantly being refined. This works because it prevents the AI from getting stuck on the first good-looking answer it finds, which might not be the best overall answer. It's like exploring all your options before committing to a major decision. The wider the beam, the more possibilities we explore. But of course, a wider beam also requires more compute. It's a balancing act. Beam search is powerful, but it's still fundamentally linear. What if we could allow the AI to explore multiple lines of reasoning at the same time, like branches on a tree? That's the idea behind tree of thoughts. Instead of a single chain of thought, the AI builds a tree of reasoning steps. It's like a sophisticated brainstorming session happening inside the AI's digital mind. The AI explores different branches of logic, evaluates different hypotheses, and follows the most promising paths. Think of a detective investigating a complex crime. They need to consider multiple suspects, multiple motives, explore different lines of inquiry. If a particular line of reasoning isn't looking good, the AI can just ignore that branch and focus its energy on more fruitful areas. Tree of thoughts is great, but what if, instead of one tree, we give the AI a whole forest? That is essentially what the forest of thoughts method does. This technique allows the model to create multiple reasoning trees, each starting from a slightly different perspective, and then it uses all of these trees to inform the final answer. By having multiple trees, we can tap into a wider range of problem-solving strategies. Instead of one detective, it's like a whole team, each with their own strengths. All of these methods involve exploring different external possibilities. But what if the AI could also look inward at its own work? That's where self-refinement comes in. The AI generates an answer, then it evaluates its own work objectively. It identifies weaknesses and improves it, because it can now see its own flaws, just like a human editor would. It's like a writer revising their own draft. It's an iterative process of improvement. This works because the AI isn't just blindly following a single path, it's actively monitoring its own progress. And it turns out, iterative refinement is a key component in many of these powerful test-time compute methods. The model is constantly going back, looking at its work, identifying areas for improvement. That's where we see these impressive jumps in accuracy, especially on complex reasoning tasks. Have you ever used iterative refinement yourself when problem solving? Let us know in the comments. So far, we've explored how the AI can improve on its answers. But how does the AI know if its answer, or part of its answer, is good or not? Enter the verifier. Process-based verifiers judge each individual step along the way, like a super attentive tutor looking over your shoulder as you work through a major math problem, pointing out mistakes as you make them, not just at the end. This allows for precise feedback. If the AI starts to go off track, the verifier can catch it early. It's like having a GPS for reasoning. But here's where things get tricky, and it's a problem that could undermine the entire system. Current verifiers are often trained on data generated by the same model. It's like asking a student to grade their own homework. They might share the same blind spots. For example, if the AI consistently makes a certain type of mistake in algebra, the verifier, trained on its output, might also miss that same mistake. This is a big open area for research. How do we create better, more independent verifiers? We've seen these amazing techniques in theory, but do they actually work in practice? And crucially, can they help smaller models compete with the giants? To answer that, let's look at some groundbreaking research from Google's DeepMind and UC Berkeley. Researchers at Google DeepMind and UC Berkeley decided to tackle this head-on. They ran a massive series of experiments and asked, can a smaller AI model, using test-time compute, outperform a much larger model? And the answer was a resounding yes, but with some important caveats. One of the first models to demonstrate this was OpenAI's O1 model, mysteriously codenamed Strawberry. It used extensive chain of thought, but OpenAI didn't show that reasoning process in the API. Users only saw the final answer. And interestingly, the results were very uneven. O1 showed huge leaps in performance on math and reasoning tasks, but on things like English literature, the improvement was minimal. This suggests that test-time compute is especially powerful for logical deduction and multi-step problem solving. Here's what the DeepMind researchers discovered. On easier problems, or when you don't need to run the models millions of times, test-time compute can be more efficient than just building a big model. On harder problems, the giant models still tend to have an edge, for now, but the gap is smaller than you might expect. They also found that it's also key to pick and choose which test time method you use, depending on the difficulty of the task. They call it optimal scaling. It's not one size fits all. By the way, they determined difficulty by having the AI answer the same question multiple times and measuring how often it got it right. So, the implications of this are huge. It means we might not need these trillion parameter monsters for every task. The DeepMind paper also hinted at something else. Sometimes, it's better to train a smaller AI model for a longer period of time. It's all about finding the most efficient way to use your computational resources. And it's not just researchers in academic labs who are noticing this. Top industry leaders are paying attention. Lisa Su, the CEO of AMD, and Jensen Huang, the CEO of NVIDIA, predict that inference time compute will become a significantly larger market than pre-training. They're betting heavily on the idea that how we use AI is going to be even more important than how we initially train it. But here comes an interesting twist, a concept that could have profound implications. Ever heard of Jevons paradox? So you might be asking yourself, what does that have to do with AI? Well, Jevons paradox states that when a technology becomes more efficient, we often end up using more of it, not less. Think about it. More fuel-efficient cars didn't lead to less driving overall. The same principle will likely apply to AI. As test-time compute makes inference cheaper, faster, and more accessible, we're likely to see an explosion of new AI applications. And that increased demand could drive up the overall demand for compute, even if each individual task uses less. So even though test-time compute can make smaller models perform like larger ones, the overall amount of computation used for AI might actually increase dramatically. Now, let's talk about scaling. The more compute we can apply at inference, the better the results. By using these techniques, we can get much more out of our AI models. However, it's critically important to remember that test-time compute is not a magic bullet. It's a set of very powerful tools, but like any tool, it has its limitations. Test-time compute can significantly improve reasoning and accuracy, but it can't give the AI knowledge it never learned. And this brings up another key point, related to something called ultra-crepidarianism. This is a fancy word for giving confident answers outside of your area of expertise. And unfortunately, some AI models can become more likely to do this, to confidently give wrong answers, even when they should know they don't know. Time test compute alone can't solve all of that, but using the techniques we have mentioned can be a start. It can also take more time. That might be perfectly fine for some applications, but it might not be suitable for others. There's always a trade-off. You can apply many of these powerful test-time compute techniques to open source models too. Imagine getting a near state-of-the-art results on your own hardware. That's the promise of combining open source models with test-time compute. It democratizes access to powerful AI. So, what does the future hold for test-time compute? It's a rapidly evolving field, but we can already see some exciting possibilities. Imagine a future where AI is more like a collaborative partner, capable of deep reasoning, self-reflection, and continuous improvement. How can we make test-time compute even faster and more efficient? Can we combine test-time compute with other powerful AI techniques, like tool use or knowledge retrieval? We can also connect test-time compute to active learning. In active inference, the AI identifies the reasoning steps or the parts of the problem it's least sure of and explores those further. And how will all of this affect the costs and accessibility of using advanced AI? Test-time compute can make AI decision-making far more transparent. We can see why the AI reached a particular conclusion. We might see a shift away from these monolithic, do-everything models towards smaller, more focused AIs. By reducing the resilience on massive compute resources, test-time compute could make powerful AI tools more accessible to a wider range of users. So, test-time compute is turning the AI world upside down. It's trying to prove that smart beats big, that efficiency can rival brute force, and that understanding the AI's reasoning is just as important as the answer itself. We're entering a new era of AI. Want to unlock the power of AI? Our free newsletter gives you the tips, trends, AI news, and tools you need to succeed. Sign up with the link in the description below. Your journey doesn't stop here. Watch our next video right here and keep building your knowledge.